Hello everyone, and thank you for watching this video on the abstraction of multilanguage semantics. I am Samuele Muro, I am a PhD student from Verona, and this is a joint work with Roy Kroll from University of Leicester and Isabella Mastroeni from University of Verona. I would like to begin by introducing some context. In the classical program of static program analysis, you have an analyzer for a programming language L, a program P written in L with meaning in some semantic domain C, and a semantic property S, usually referred to as a specification. The goal of the analyzer is to try to decide if your program P meets the specification S. In this talk, we drop the assumption that the program P is entirely written in a single language L, and instead we assume it is a multi-language program, partly developed in a language L1 and partly in L2. Or another way to put it is that we assume that the language L is actually obtained by blending two different languages, L1 and L2, with P a program in this new language. The goal under this new setting is to develop an analyzer for the multi-language L1 plus L2. However, we don't want to redesign the new analyzer from scratch, but instead we would like to combine existing static analysis of the underlying languages in order to obtain the static analysis of the whole multi-language. Okay, some reasons why we are interested in this problem. There are a lot of existing programming languages and libraries, and programmers often exploit cross-language interoperability mechanisms to achieve code reuse or to use features from one language into another. Let me give you some examples. In the Android native development kit, programmers make use of C or C++ libraries within Java or Kotlin code, which is an example of code reuse. Or from Java 8 onwards, programmers can embed the JavaScript code within Java through Nashorn, which is a JavaScript interpreter developed in Java. In this way, they exploit the characteristics of JavaScript, of being an interpreted language, in order to modify parts of the Java application without the need of doing a full new release. And of course, there are many other examples. So the overall message is that software is no longer developed within a single programming language. And therefore, if we aim to analyze multi-language programs, we need to study abstractions of the multi-language semantics. I mentioned several times the word multi-language, but what exactly are multi-languages? In previous works, we studied a theoretical framework for modeling the combination of programming languages. From a very high-level perspective, starting with two languages, L1 and L2, we are able to produce a new language, L1 plus L2. That is a multi-language. Programs in this new language are obtained by applying cross-language substitution. What does that mean? Suppose to start with an L1 term, f of t1 to tn, and an L2 term t. Then we can replace one of the ti subterm, which are written in L1, with the L2 term t, and obtain this new multi-language term. As you can see, t is introduced by a new operator symbol, which is called a conversion operator, because it moves terms across languages. Let me give you a quick example of a multi-language term. This is a valid program in the multi-language obtained by combining a while language with the simply typed lambda calculus. As you can see, the overall term is an assignment, but the right side is not a while expression, but it has been substituted by a lambda application. The main contribution of the paper is a general technique for abstracting multilanguage semantics once given the abstract semantics of the underlying languages. Since the multilanguage framework is based upon the theory of order-sorted algebraic signatures and algebras, we have taken some intermediate steps. First, we have defined the collecting and abstract semantics in terms of algebras over a signature. Then we have defined the notion of collecting semantics for a multilanguage. And finally, we have combined the abstract semantics of the underlying languages into an abstract semantics for the multilanguage. Before talking about collecting semantics and abstractions, I will review the basics of the multilanguage framework. In this framework, syntax and semantics of programming languages are given by order-sorted signatures and algebras. A signature SG is specified by a set of sorts S, whose members may be understood as syntactic categories, a subsort relation on S, which is used for proper handling excuse me, several types of polymorphism, but I won't talk about polymorphism here. If you are interested, you can find all the details in the paper, and a set of sorted operators, which can be either constant key with some sort S, or function symbols F, which can build terms of sort S provided with n terms of sorts S1, S2 to Sn. So, for instance, in a simple imperative language, the skip command can be declared as a constant of sort com because it is built from thin air, and a loop command is a function symbol which takes an expression that is the guard of the loop and a command, the loop body, and so on. Then an algebra provides a signature with meaning, and thus we have an interpretation set for each sort S in SG, and an interpretation function for each operator, which defines the semantics of constants and function symbols. For instance, in this example, we are providing a denotational meaning to each of these operators. Now, a multilanguage signature is defined by taking a pair of order-sorted signatures and by specifying interoperability relation between the sorts of SG1 and SG2. So, an interoperability constraint between S1 and S2 means that we want to use SG1 terms of sort S1 in place of SG2 terms of sort S2. And therefore, we add a new conversion operator to the multilanguage from S1 to S2 that moves terms across these languages. Then, a multilanguage algebra C is given by an algebra C1 over SG1 and an algebra C2 over SG2. So this means that we are taking the meaning of the underlying languages. And plus, we also have to provide a translation function for each conversion operator. So this means that if we want to use S1 terms in place of SG2 terms, we have to provide a translation from the interpretation set of S1 to the interpretation set of S2. We are now interested in solving the following problem. Given an SG algebra C, we want to define a new algebra C star which computes the strongest program property for each program P generated by SG. So it means that C star has to satisfy this equation, and therefore C star is the collecting semantics in the most general sense. The definition of C star is quite straightforward and boils down to the application of the power set functor to both interpretation sets and interpretation functions of the algebra C. Okay, let's move to a slight variation of the same problem. Suppose that C is actually a fixed point semantics, and we ask if we can get a fixed point definition of the previously defined collecting semantics C star. The answer is yes, and it goes as follows. We start by defining the right semantic domain in which to provide the fixed point computation. So the carrier set of this domain is given by the properties over C, and the computational order is obtained by injecting the original domain below the flat ordering for all non-atomic elements. Let me give you a small example. Suppose that C is the set of natural numbers equipped with the usual algebraic order. Then the domain we are constructing is given by preserving the original domain and putting everything else above. Then we define the new semantic transformer F star as the lifting of F induced by the power set factor, where F is the semantic transformer on the original domain. So F star is monotone because so is F, and we can actually prove that its transfinite iterates are well defined. Finally, by an application of the Kleinian fixed point transfer theorem, we can move the fixed point construction from the starting domain to the collecting semantic domain, and we can prove the chain of equalities. Let's now face the same problem, but in the multi-language world. So we start with a fixed point semantics given by a multi-language algebra C, and we want to obtain the multi-language collecting semantics C star. So C star has to compute the strongest program property for each program P, and we want it to be definable through a fixed point computation. So first, let's just define C star. We need to provide two order sorted algebras for the underlying languages, and we take the collecting semantics C1 star over SG1 and C2 star over SG2, and we lift the interpretation functions of the conversion operators. Now, does C star admit a fixed point definition? Well, it depends. But if C1, C2, and all the conversion operators admit a fixed point definition in C, then we can actually prove that so does the multi-language collecting semantics. Now that we have a suitable definition of multi-language collecting semantics, we want to define the notion of abstract semantics, first in the algebraic world of the sorted algebras, and then in the multi-language setting. So let's see the standard semantics of the language SG and see start the corresponding collecting semantics. We say that an SG algebra A is abstract if it is equipped with a concretization function from the carrier set of A to the carrier set of the collecting semantics C star. Moreover, we call A sound if its operator soundly approximate the concrete ones, which is encoded in the two expressions below. Finally, as one might expect, sound algebras induces sound semantic functions. Okay, so let's move to the abstract semantics in the multi-language world. So now C is a multi-language algebra over the multi-language signature capital SG, and C star is the multi-language collecting semantics. Recall that a multi-language algebra is given by a pair of order sorted algebras plus the interpretation of the conversion operators. So we call any SG algebra A abstract with respect to C if both the underlying algebras A1 and A2 are abstract with respect to C1 and C2 respectively. Similarly, we say that A is sound if A1 and A2 are sound and if the semantics of conversion operators correctly approximate the concrete ones. Under this hypothesis, we can prove the same proposition as before, but in a multi-language context. So if A is a sound multi-language abstract algebra, then it induces a sound multi-language semantics for each multi-language program P. Okay, so what's more in the paper? In the same way we investigate the soundness of multi-language algebras, we have also studied the forward and the backward completeness. Moreover, we have instantiated the framework on a simple combination of two imperative languages for which we have two sign analysis. Then, given any multi-language program such as the one in figure, where the two languages are depicted in different colors, we are able to compute its multi-language sign semantics obtained by combining the two sign semantics of the underlying languages. So, to conclude, in this talk we have shown how to combine abstract semantics of single languages in order to obtain an abstract semantics for the multi-language. And in doing so, we have lifted several concepts of abstract interpretation to the multi-language world. So let me spend a few words about future research. In first place, we are going to apply the developed theory of multi-language abstraction to the categorical semantics that we developed in MFPS 2020, and we also aim to implement first prototypes of multi-language static analyzers. Thank you for your attention.